So we're going to switch gears in a pretty serious way for Chapter 16. We're going to switch straight into spectroscopy, meaning no more reactions for the next week or so. Nmr Spectroscopy is my favorite spectroscopy, and arguably it's the most powerful form of spectroscopy you have in organic chemistry. If we think about IR spectroscopy, it told you a lot about functional groups. If we think about mass spec, it told you the molecular weight. It told you a little bit about structure in terms of fragmentation patterns. But ultimately, we were kind of limited with our ability, right? We didn't know a lot of the structural isomers because when you get into large, complicated molecules, it just gets too complicated. NMR tells you a lot more information, and it tells you roughly how atoms are connected in a large molecule. So let's take a look. They changed this on me. Oh my goodness. Sparkle fan. Okay, so if we look at NMR spectroscopy, it's based on a really simple principle that atoms or nuclei with an odd number of protons or neutrons have nuclear spins. We're not really going to get into the physics behind why they have spin. That's something you would discuss more in physical chemistry. But most of you guys have taken physics, right? Have you guys gone into electricity and magnetism? Some people? All right. How many of you guys remember the hand rule? Oh my goodness. That's like the best part of physics. The hand rule basically says anytime you've got a spin, you can actually create a magnetic field. So if you've got a charge that's spinning, it actually generates its own magnetic field. So let's take a look at a really simplified view of a nucleus. We know the nucleus has a positive charge. And if this nucleus is spinning around in space, you can imagine it is rotating something like this. All of a sudden, what will happen is it will start generating a magnetic field going kind of north and south. So, what's that? Oh, I'm just drawing kind of magnetic field lines. So up here we've got our north pole, down here we've got our south pole. And depending on the nucleus, the strength of this magnetic field will vary. So we actually have NMR for protons, we've got NMR for carbons, we've got NMR for everything all the way through platinum and super heavy atoms. We have to use a different experiment depending on the nucleus that we're investigating, though, because obviously nucleus of different atoms are of various size. So you can imagine in a solution, you've got a bunch of these atoms, their nuclei are spinning around in a bunch of different angles, and we need to actually align them in a magnetic field. So I'll show you guys a really simple way of viewing magnetic resonance using a compass. Hopefully this will open. So you can imagine your nucleus, because it's got a north pole and south pole, is similar to a compass. And what you can do is you can try to align all of your nuclei in an applied magnetic field. So I'm going to apply a magnetic field here using a larger magnet around my nucleus, right? And then what I'm going to do is I'm going to actually try to hit this compass so that it knocks it off axis. And so in order to do that, I actually have to create a perpendicular magnetic field that will come hit it from the side. And the easiest way to do this is actually using electromagnetic radiation in the form of radio waves. So what I'm going to do is I'm going to apply a magnetic field to the side. And you can see I've knocked that nuclear spin off axis a little bit, right? What NMR does is it will apply this electromagnetic frequency at a certain, this magnetic pulse at a certain frequency. And so imagine here, I'm going to start changing the frequency. So now this magnet's coming and trying to nudge it off axis. You can see it's a little bit like pushing a kid on a swing. Right now we're pushing it way too slowly. And if I really crank it up, it's kind of like hitting a kid too fast on a swing. You got to catch them at the point where they're coming right back at you. And so that's called the resonance frequency, is that frequency at which you're pushing that nucleus off axis and it's really starting to wobble a lot. So let's try to find the resonant frequency of this nucleus. And so I'm going to slow this down a little. And you can see right now, even though I'm going at a relatively low frequency, I'm actually able to knock this off axis a fair amount. And so we call that frequency at which you're knocking it off axis the most the resonant frequency. And every nucleus has a different resonant frequency. And this tells you quite a bit about the location of that nucleus relative to other nuclei within the molecule. It's a little bit abstract, but let's think about it too in terms of a spinning sphere. So you can imagine a spinning sphere will actually try to whip back into that magnetic field as soon as that frequency stops being applied. So you can imagine that horizontal frequency knocking it off axis, right? It's going to be wobbling off to the side, and then as soon as you stop, it's going to relax back into that magnetic field. So essentially what you're going to do is when you look at this, we're knocking it off, knocking it off, knocking it off, knocking it off, and then all of a sudden we're just going to stop the magnetic field and then basically observe how it relaxes back into the larger magnetic field. And so that's kind of the nuts and bolts of how really simple NMR experiments are done. Has anybody ever had an MRI done? MRIs are actually the same exact technology that's used in Nmr spectroscopy. The reason they're called MRIs is because patients really don't like being stuck inside a piece of equipment that has nuclear in the title, right? Kind of weirds people out. So it's the same idea with MRI. We're just basically aligning all of your nuclei as a human being in a magnetic field and then using radio waves to knock those nuclei off axis. Then they'll spin around and whip back into the magnetic field, and we're observing how they relax back into the magnetic field. All right, so let's really briefly summarize how this works, and then we'll get into the nuts and bolts of NMR. I'm angry at Microsoft for changing all of this. So we align nuclei in a magnetic field. And then a second perpendicular EM pulse knocks the nuclei off axis. And then the detector records the nuclei relaxing back into the field. So when you look at the actual spectrum for an NMR, it looks crazy complicated. So I'm just going to draw the true spectrum. And essentially, if you've got a nuclei that's off axis, it's going to whip around in this really big frequency, and then it's going to kind of flatline like that. So imagine this spinning nuclei is whipping around like a lasso and then relaxing back into that parent magnetic field. This is called a free induction decay. This is also referred to as an FID. This is too complicated for a human being to look at. So instead of looking at the free induction decay, we typically use a computer program that will do a transformation, a Fourier transformation, so that we actually get normal looking signals out of it. Yep.
What's that word right there?
Which one? Oh my goodness. Dector. You can give a guy a PhD, but you can't make him spell right. All right. So let's take a look at how the NMR works from a spectra point of view. And this is pretty simple. So nuclei in the same chemical environment have the same chemical or have the same resonance frequency. So let's take a look at a really simple example. So I've got a hydrogen here, I've got a hydrogen here, I've got a chlorine here, and I've got a chlorine here. So this is dichloromethane, right? We've got two different protons coming off of it. And for the most part, we're going to be looking at the protons in our molecules, and I'll teach you later about the carbons too as well. But for the majority of this chapter, we're going to be focusing on the protons. If we look at these two protons, are they in the same chemical environment, or are they in different chemical environments? What do you guys think? Yeah, exactly. If we look at this, they're both in the same relative position to the chlorines and the carbon as the other one, right? So in this case, we could look at both of these and we can say, you know what, HA and HB are in the same chemical environment because of the overall tetrahedral shape. Therefore, we only observe one signal. If we had protons that were pointed in different chemical environments, then we would observe two signals. So we want to try to figure out how many unique sets of protons we have in our molecule. In this case, we only have one unique set, even though there are two protons that make up that set. Let's take a look at another one. So we'll do dimethyl ether. So we've got two CH3 groups coming off. How many protons do we have that are in their unique chemical environment? So how many unique sets of protons do we have? Okay, so let me ask you this. I got a question for you. I'm going to just label this proton, proton A. Why is proton A the same as this proton down here?
Sigma rotation.
Sigma bond rotation, right? If you think about this methyl group, it is spinning around like a helicopter blade. There's equal probability of proton A being in that position as proton B, right? It's spinning around so quickly that the NMR can't tell the difference between proton A and proton B. All right, so they're in the same chemical environment, which means all of these could be labeled as set A. Okay. What about the protons on the other side? Are they the same or are they different? Or are they different? They're the same, right? Why are they the same?
The shades.
Because of symmetry. If we look at this, there's a symmetry element going up and down, right? That means that the left-hand side of the molecule is in the same chemical environment as the right-hand side of the molecule. So if we look at this, even though we've got 6 protons, they all are in the exact same chemical environment, which means we only observe one signal. All right, what about the carbons here? Are the carbons equivalent? Yeah, exactly. Because of symmetry, the left carbon is the same as the right carbon. If we were to look at this using carbon NMR, we would again only see one signal because there's only one type of carbon in this molecule. All right, you guys ready for more challenging stuff? All right, let's go to some harder ones. Okay, so for the harder example, I'm going to do ethanol, everybody's favorite alcohol. And we've got a bunch of different protons coming off. And what I want you guys to do is to try to decide how many unique sets of protons you have in ethanol and how many unique carbons you have in ethanol, and then discuss it with your neighbor and see if you agree. All right, so let's take a look at ethanol. If we look at this proton coming off the oxygen, are there any other like it? No. So it is unique. There are no other like it. So we're going to highlight that as HA. All right. And the next one, I'm going to switch to blue. And I'm just going to go down the molecule and I'm going to say, all right, this proton, are there any other like it? Which one?
The one at the opposite.
Yeah, the one coming towards us, right? If we think about ethanol, we can cut it in half through all three carbons in the all two carbons in the oxygen. That blue hydrogen is in the same environment as that hydrogen, right? Because there's a plane of symmetry going through the molecule itself. Okay? And then last but not least, are there any others like this? Yeah, the other two, because we said methyl groups spin like helicopter blades. So in this case, we've got 3 unique proton signals that we should observe in our NMR spectrum. So we should observe 3 different NMR signals. All right, what about carbon signals? How many carbon signals should we observe? 2, exactly. All right. So let's try an even harder challenge. Throwing you guys softballs. And then we'll expand upon this a bit more too.
Too hard. Pretty sure you made that up.
What's the question?
How many proton signals should you observe? And how many carbon signals should you observe? And then check with your neighbor.
These ones. So
And I'm going to draw in all of our hydrogens just because I want to box them.
1, 2, 3.
No, I didn't think so.
No, so this is the same as this. But this is different. These are different. No, this is
So what is that red?
Definitely
but
keep
they're
it
in 6 positions because they're one way.
Maybe 3 carbon.
I don't know. I don't want to be wrong. I haven't been wrong. There's resonance. I feel like resonance shouldn't affect me somehow.
I've heard a few people ask about resonance or the positioning of the double bonds. It's really important with benzene rings to remember that all of those carbon-carbon bonds are the same, right? So oftentimes with benzene rings, what you might see is somebody drawing them with a circle. That's fine. They're all equivalent. So don't treat them as being in different chemical environments. And then give me a thumbs up if you're agreeing with your neighbor.
We're agreeing.
From the bottom and the tip at the top should be the same. Yeah. And then the hydrogen's coming from
I don't want to be wrong.
The other hint we know is that methyl groups, because they spin around like helicopter blades, are all equivalent, right? So I kind of lumped all of the methyl groups together as CH3 groups.
maybe 3 carbon groups.
Yeah, so 2 and 3. Yeah, that makes sense. I forgot about it.
You're saying 2 or 3? You're saying 3 or 2?
That has to be wrong all the time.
2 and 3? What do you mean 2 and 3? Explain that.
2 hydrogen groups and 3.
Okay, so let's check. I'm just going to arbitrarily box one. I want you guys to help me find others that are like it. So the protons coming off this methyl group, are there any other like it?
Yes.
Which ones?
All of it. All of it.
All of the methyl groups. Okay, so if I box these protons coming off here and these protons coming off here, they're all equivalent because essentially we've got a helicopter blade of helicopter blades, right? It's a little weird to think of it that way, but a terbutyl group has 3 different methyl groups, all of which can be spinning around, and each of them are spinning themselves. It's a little abstract to think about, but because of that sigma bond rotation, they're all occupying that exact same chemical environment. All right, are there any others like those?
Yep.
Yeah, down below. If we think about it, right, we've got a symmetry element that's cutting this molecule in half, which means the top side is identical to this bottom side. So all of these red protons are in the exact same chemical environment. Okay, so let's go ahead and box these blue ones. Are there any other like it?
Yes.
Which one? The remainder, right? If we think about the symmetry element going horizontally, we know the top half and bottom half are equivalent. And we've got a symmetry element cutting the molecule in half this way too. So we can cut it in half twice. We have two symmetry elements within one molecule. Okay? So even though this molecule looks frighteningly complicated, there are only two signals that you should observe. It's a little abstract to think about. So let's take a look at this. Oh. Sorry, let me switch back here. So two different 1H signals. All right. So if we look at this, I'm going to show you guys kind of what the NMR spectrum might look like. You have this scale going horizontally, and the scale is measured in parts per million, or ppm. And the scale typically goes from about 15 to 0. And so I'm going to put some markers in here. And we only expect two frequencies. We expect frequencies for the blue protons and for the red protons. In this case, do you think they're going to be roughly the same size peaks, or which peak do you think is going to be bigger?
The red ones.
The red ones, why?
Because there's more of them.
There's more of them, right? So you've got more nuclei absorbing signals, which means they're going to emit a lot more of a signal when they relax back. So if we look at those red protons, they'll show up typically in this region, and this peak would be huge. It would be a big, massive peak. And this would have a relative size of 9. So we oftentimes refer to that as integration. It's the area underneath the curve of the peak. So if we were to go ahead and shade this area, the area underneath that peak would have a relative size of 9. It's unitless. It's just used when you're comparing it to other peaks in the same spectrum. Yep.
Is there any relation to that to the number of hydrogens, or because there's 18 of them?
Oh, yeah, in this case, let's change it to 18 just so we're consistent. So we've got 18 total protons for that red box set. All right, and then the blue protons are going to show up at a slightly different resonant frequency. Typically, they show up at a higher ppm, and we've got 4 of them. So in this case, we're going to have a much, much smaller peak. And the area underneath this curve will have a relative size of 4. We're going to talk about that later. I just wanted to introduce the idea that the size of your peak corresponds roughly to the ratio of protons. So if we look at this, we could say 9 and 2 is the ratio, 18 and 4 is the ratio. It really doesn't matter. It's just a ratio of your peak sizes relative to one another, right? All right, let's do a harder one. All right, this one's a little bit weird, but I'll give you some time to think about it and then talk about it with your neighbor. So we've got 2 fused rings. And in this case, I'm going to put a chlorine here, a chlorine here, and a bromine. How many proton signals should we observe for this molecule? And I'm going to go ahead and draw in the remaining hydrogens.
assuming those two should be the same.
I see four, I don't see one.
But this one came out is giving a different spectrum.
Oh wait, no, I see. Yeah.
I was like, what the?
1, 2, 3, 4.
Oh, geez, I don't want to hear it.
Mine's full though.
I'm not sure if you I'm not sure. Yeah, I feel like it's different. So 1, 2,
Four was in violet. You don't understand. We have 3 exams. We have 2 more. We have a lab exam. So 4 exams. We have a lot of exams. And his exam is rough.
All right, give me a thumbs up if you guys think you got it. A few people? All right, let's do this as a group. I want you guys to help me out. Are there any protons like that red proton?
Yes.
Oh, disagreement.
Oh, the bromine.
I like arguing.
Oh man.
So let's do this.
Nah, bro.
Is that red proton the same as the proton on the underside of the ring? Why not?
Bromine.
Yeah, if we look at that top proton, it is closest to the chlorine. If we look at the bottom proton, it is closest to the bromine. They're not in the same chemical environment. So oftentimes when I'm labeling these, I like to just use a really simple scheme where I just label it this one HA. And we know HA is different from HB. What about this proton over here? Are there any other protons like this proton?
No.
I mean, it's close to A.
No.
So if we look at it, it's close to A. Is there a symmetry element in this molecule?
Yes. No.
No.
Can we cut it in half horizontally? No, because the chlorine's on the top half and the bromine's on the bottom half. So we can't cut it in half horizontally. There's no horizontal symmetry element, which means that this proton is on the side of the ring closest to the chlorine still, and this proton's on the side closest to the bromine. So in this case, we've got 4 unique protons coming off of that benzene ring. All right? If we look over here, are there any protons like this proton, the one coming off the carbon where the bromine's attached? No, there are no other protons that are also attached to a carbon that has a bromine, right? So we've got A, B, C, D. We'll call this one HE. And then the tricky one, those last 2. Raise your hand if you think they're equivalent. Raise your hand if you don't think they're equivalent. Ah, that's pretty evenly split. All right, let's think about it this way. I'm going to box these. So I've got this blue box, and I've got this red box. If we look at that blue proton, you guys notice how it's cis to the bromine? If we look at the red proton, it is trans to the bromine. They are occupying different chemical environments, and there's no way to rotate the sigma bond Y. Yeah, we've locked it into a ring. Rings can't have that sigma bond rotation, so they can't flip around and occupy the same space. So they're actually in different chemical spaces. So if we look at this one, it's pretty abstract to think about. But we've got A, B, C, D, E, F, and G. And so let's take a look at these. These are referred to as diastereotopic protons.
You made up that word. Diastereotopic.
Sounds good.
So one we said is cis to the bromine and one is trans. That means they're in a different chemical environment. So if we add up the number of unique protons we have 1, 2, 3, 4, 5, 6, 7 unique sets. So I'll show you guys an easy trick for identifying diastereotopic protons. And I'm going to draw these out twice. is when you are wondering if a pair is diastereotopic, change one of them to a deuterium atom. So for this example, I'm going to change this one to a deuterium atom and this one to a hydrogen. And I'm going to compare it to the opposite. So for my other example, the deuterium is going to be a dash. What's the relationship between these two compounds?
Maybe the diastereomers.
Maybe they're diastereomers, hence the name diastereotopic.
Throwing it out there.
Don't forget the chlorines.
Oh, thank you.
In the different molecules.
So it's a really easy thing to do anytime you're stuck is try to change one of the two to deuterium and see what the relationship is between your two molecules. That's simply why they're referred to as diastereotopic. They're completely different, just like diastereomers are completely different, right? All right, we've got a few more minutes. What I would recommend doing with this time is try to grab a pod and go through the first couple problems with the partner and make sure that you're on track. And I'll float around the room too and help you guys if you're stuck.